Yeah.
All right, I don't know if you can see this well. This is what I have so far for my, so you're gonna put that one on? Or?
Yeah.
My mirror cell. It's kind of a different design. I can't see.
Come up to this.
Oh,
Yeah, hold it up against the black background. You can see it.
yeah.
Let me pin that.
Highlight this.
I'll pin that in.
Spotlight.
Oh, there you go. You got it.
Put that full screen again.
I didn't think I changed it, but
You did.
And I'm still on.
you go. Are you pinning it or am I?
We're on the wrong mic. We're on the wrong camera.
Yeah.
You're getting but
Well, we'll get it in a minute.
Oh, okay. There it is.
All
All right. So I don't know if you can see how this moves. I tilt it.
that's speak about this period.
Yeah. So anyway, this design allows for all the motion to be centered around the center of the mirror. So the center of the mirror doesn't actually move at all.
I'm fiddling with the sound.
It'll be better when I actually get the screws, drill the holes for the screws, get the screws in there, look a little more. But anyway, it's a work in progress. All right, so can everybody hear me now?
Yes.
All right. Let's see. Okay. So you can get the. All right. So diffraction. When I was in high school.
Eric, stop playing with the camera. Oh, maybe he was busy.
We were fine before.
Okay. It's like the early days of
There we
television.
go.
It is.
Yeah, here we go. All right. So
Not touching.
in science class in high school, they taught us about diffraction, and they used a shallow pool of water. And here are the waves. It has an oscillating bar at the end, and it's moving back and forth, and it's causing waves. And they show how when you have an obstruction, the waves go by, but you get a little bit of faint weak waves like this, and that's diffraction. Waves curve around this edge and they spread out. Light does the same thing. It's kind of an oversimplification, and I didn't realize that at the time. They tell you that the wave particle duality of light, and you kind of have an idea of what that means. But when you have an aperture, let's say like James Webb, how all the mirror segments are hexagonal. Each one of these edges, as the light's coming in, it's not going through it like a lens, but it acts the same way when you have the edge of an aperture. And the light going through here, kind of, it's saying it's coming straight on. It curves around the edge, so it's each edge is diffracting light. And if you now when this comes to focus, what you would end up with is a very, very tiny hexagon. Your airy disk is not a disk because you're hexagonal, and each of this, all the light that is spreading out this way gets focused. That one creates a diffraction spike, and that one creates a diffraction spike that way, and each one creates a diffraction spike. And so that's why you get such a bright diffraction spikes on a non-round aperture. So if you have a round aperture and it's doing this all the way around, then what you get is your little airy disk and diffraction rings, but you also get it's organized into rings when it's round. But if you have even one hair going across, all the light that passes that, you get diffraction around both sides. This side, you get diffraction when it comes to focus. It comes down to a line. The light coming off this way gets squeezed down, and it all gets concentrated into a line. And of course, it has two sides, and you get a diffraction spike the other way. If it's only halfway across, you still have the same thing. You have diffraction spikes going off both sides. They're half as strong, but you still get the same effect. So that's why when we were looking at the James Webb, how I think two of the supports were like this. This one's parallel to this one's parallel to this one, and there's one that wasn't parallel. I forget how it wasn't parallel to any of the side, but it wasn't. So it created its own spike, and you had another faint spike like that. So anyway, that's why you get that. The weird thing about diffraction is that you can have one obstruction here. If it's a hair, you get very weak diffraction spike. If it's a thick bar, you get much stronger diffraction spikes. Why? Because both sides is throwing off a diffraction spike, and this is kind of backwards. In other words, this side is actually throwing the light that comes in bends around this way. So it's actually this side creates a diffraction spike coming out this way, and this side creates a diffraction spike going the other way. And the strange thing is with light, and I didn't know this in high school, was that when you have a wider obstruction, it disturbs the light more. Now, you would think you're just blocking more of the aperture, you get less light through, this will be that much less bright, but it doesn't work that way. When you have like the classic double slit interference, when you have an obstruction, break, you have waves coming through, you get and then each one has diffraction. You get interference. And you get when it finally hits the screen, you get bright and dark bands. Brighter here, a little less, but you get nothing in between because it's hard to illustrate this easily. But anyway, you get constructive and destructive interference, and so you get the same thing here, but you get much less of it when it's thin, and much more of it when it's wide. And the weird thing about light is you have to realize that it's not like water, where you have a wave front going through there comprised of billions of molecules of water moving as a wave. You have one photon, every photon goes through by itself. There is no interference with other photons. Every photon interferes with itself. They found that when you do this experiment with electrons, they also have wave particle duality, and you can actually tell which, you can measure where an electron goes through one or the other slit. And they find that you can actually slow it down so that you have only one electron at a time. And you know you only have one at a time. And it still builds the same pattern. You don't get electrons going through straight. So every electron interferes with itself. And you have the same thing. When you're going, when the light is passing through here, it's the only way for it to form a pattern, which is brighter diffraction spikes when it's wider, and fainter diffraction spikes when it's thinner, is if the light is interfering with itself. Every photon that goes through here and diffracts around this way, if it's a wider obstruction, it will diffract more often. And the only way to visualize that is that it's actually going through the whole aperture all at once. The entire photon is a wavefront going through all of it all at once. Every photon does this. And it gets even weirder when you realize that you can have another aperture over here, creating another image and combining them into a much higher resolution image with interferometry. You can do that with optical interferometry. And every photon that goes in this side, the wavefront also goes in the other side. Where does it end? How big is that wavefront? You could do this theoretically with, a billion miles apart, if you're looking at something a billion light years away, and it's still going to go through both apertures and create an interference pattern. Every photon goes through by itself. That's the real weird part, I think, about diffraction, about light. But I don't know. I hope I've made it clear as far as how you get diffraction spikes. You have light that curves around, bends around every obstruction and creates, you get a diffraction pattern. And actually, if you have a telescope with a front lens like this, and then a smaller rear lens, and light's coming through and comes to a focus here, if you have light coming off axis, how can I do this? If this, all right, this is too big. If this is a little smaller, the light coming straight in goes through both. The light coming through at an angle might miss this one. So what you end up here when you look at, if you're looking through the lens, if you're looking through the back and you're just looking straight through, what you see is, you can see the rear lens, but then you can only see part of the front aperture. You can only see maybe this much, because the rest of it, it's at an angle. It doesn't. Anyway, when you get off axis in many telescopes like this, the aperture's not round, and what you have, on center, you have a regular, diffraction pattern on bright stars. But when you have, and it's kind of on really bright stars, it just kind of looks like this, it's just flaring. But when you have what looks like a kind of an almond-shaped aperture, because it's vignetting, you get diffraction off of two surfaces. And what you end up with in the center is it's a bright star, and you get diffraction like this, but there's no diffraction here, so you get a blank spot. And I've even seen this in Hubble images where there's absolutely no diffraction on two sides of the star, just because the light is kind of the way it focuses. The light that reaches that point is coming from a non-round aperture. So I don't know. Does that help? Does that help clarify anything, or just make it work?
I'm not sure yet. Oh, I think about that one.
Well, it makes me wonder, how big is a photon?
Yeah,
If it's gonna go
exactly.
through both apertures.
Yeah,
Photons are actually waves.
Waves,
As you
right.
said, they behave like particles when they interact
when they
with
interact,
something.
yes. Oh,
But
and
they
the other.
behave like waves when they travel.
And the other really weird thing about this is when you have electrons going through here and you set up a detector, you can even set up a detector here. If you turn it on so that you know which aperture it came through, then you do get simply two bright spots. You do not get the interference pattern. And if you detect it with a computer and it's collecting the data, and you turn on a scrambler that does not read out, it's still detecting it, but it's not displaying it, you get the diffraction pattern back.
No. That's what messes my head.
Yeah.
All right, thank you.